That song sounds so much better on a sitar. But it's kind of fun. That's Beatles. Norwegian Wood. Very old song. Beautiful song by the Beatles. Okay, so to get going on the next part of this, we're going to look at trig equations that have multiple angles. So what I mean by this is things like sine of 3x, 4x, x over 2. The argument's changing, so the period's changing, and that's kind of the key thing, is we're dealing with trig functions where the period has changed in some way. Okay, now this is kind of the process you want to go through, and I think it's real important when you're doing these multiple angle equations that you follow this procedure exactly as I've got it lined out for you. Isolate your trig function. Take the inverse of both sides. We haven't done that yet, but we're going to do that on this. And then remember that if you're dealing with a sine, cosine, secant, or cosecant, the period, the formula is generally 2 pi over b. So we're going to use 2 pi within this problem. If it's a tangent or cotangent, then you want to use pi for the period. Okay, once you do this, you'll solve for x, you'll get a general formula. Then if you want to get specific solutions, you're going to vary the k. So you're going to be starting by getting a formula on these problems. And then if you're asked to get specific solutions, then you can vary the k and get as many solutions as you want to, or get the solutions on a prescribed interval. And then we'll check graphically like we've been doing, and I think that's real important when you're doing these problems in particular. So I'll go to the next page, and we'll go ahead and start by crunching out a few of these. And these two right here, the first step is to isolate. And in this example, both of these examples here, you're already isolated, so you don't have to worry about that. That just means the trig function is isolated on one side of the equation. So what we're going to do on this first one, you want to write down that we're taking the inverse sine of both sides of this equation. So we want to get this kind of taken care of, and then we'll start looking at the unit circle when we do that. Okay, so one thing I want to mention on this, you may remember the range of an inverse sine was from negative pi over 2 to pi over 2. So if you were doing an inverse sine, you were only generating answers on that interval. You really ignore that on these problems. So you really ignore that range of the inverse sine because you're trying to get a formula for all solutions everywhere. So you don't pay attention to that. So what you're going to do is, what will happen is when you do the inverse sine of the sine, it will undo that operation, and that'll just give you 2x. That's conceptually the same thing as if you take the square root of square, you're undoing the operation. I mean, you do this kind of thing all the time in math. You're undoing an operation. Okay, so what happens on this one is we're going to find on the unit circle where the sine is square root of 3 over 2. So that happens in radians in 2 places. Okay, so what we're going to do is the first solution, bring down the 2x and just write pi over 3. Now you're going to put plus 2 pi k, where k is represented by an integer. And then in a minute, we'll solve this equation for x. Okay? The other possible solution is 2x equals 2 pi over 3. And again, we start by saying plus 2 pi k, with k being an integer. So what we're doing is the period of a sine is 2 pi. So we're just kind of saying, okay, another lap around the circle is going to keep giving us the same solution over and over again infinitely. But what we're going to do on this is we got to solve for x. So you can divide by 2. To me, it's more efficient to multiply both sides by 1/2 when you solve this equation for x. Okay, so the 2's divide out, you'll get x equals, do a distributive property, you'll have pi over 6, you multiply straight across, And then if you take half of 2 pi, so you're really doing 2 pi k over 2. 2's cross out, leaving you pi k, with k being an integer. Okay, so that is, right there, a formula for some of the solutions of this equation. We ought to solve the other equation for x to get the rest of those solutions. Okay, so we're going to do the same thing here. We're going to multiply both sides by a half. That'll divide that out, and then this time you're going to get x equals 2 pi over 6. Now if you do 2 pi over 6, that just reduces down to pi over 3. Or you could do it like this, 1/2 times 2 pi over 3. You can do this in your head. 2's cross out, leaving you pi over 3. Okay? So either way, that gives pi over 3. And then again, if you take half of 2 pi, you get pi k, where k is an integer. Okay, so that would give you another formula. And you can write those solutions separately. When you put that all together, that would give you the formula that would generate all of the solutions of this equation. Okay? Now this says find all real number solution. All means formula. And real number means radians. Okay, that's how I know to use radian measures, because of the directions. Okay? All right, let's get your calculator out and let's learn how to verify this on the calculator. And what I'm going to do on this is probably have you do this like this. Let's put in the calculator. Let's put in y1, put the left side of the original equation, which is sine of 2x. And in y2, put the right side of the equation, which is square root of 3 over 2. So you want to get that put in. I'm going to slide over here kind of to the side, so I'll have room to just put all this stuff on here. So you want to get that in your calculator. For a window, what I'm going to have you do on this problem is go negative 2 pi to 2 pi. We can do it this way. You can scale by pi over 2. And then we can make the window, negative 4 to 4 should be fine on this, so I'm just going to have you do the window like that. You also want to make sure that you're in radian mode on this problem now. I think I'm in degree mode right now. So get yourself in radian mode when you do that. And then if you got everything set up, you can type graph, and I'll show you kind of what's going on this problem now. Okay, I'm going to adjust one thing, because I think you'll see this better. Let's go back to the window. And let's make the y's just go negative 1 to 1. It's good enough if we just go negative 1 to 1. So let's redo the window. And then graph again. And I think you'll get a better picture of what's going on in the problem now. Okay, so that would be the graph of the sine of 2x. And what's coming across the screen now is the graph of square root of 3 over 2. So essentially what we're doing is we're finding the solutions. The solutions on this graph are going to be all of the places where these things intersect. Okay, essentially. So when we got our original solutions, we had pi over 3 and pi. I think if you look at the unit circle, we ended up, when you generated this formula, we ended up with pi over 6 and pi over 3. Okay, those were the first two original solutions to that problem. So let me show you what I would do on this. So what I would do is I would trace at pi over 6, and see that would give that solution right there. That verifies that. And then you could trace at pi over 3, and that would verify that solution. Now, you're getting infinite solutions. So what you're doing essentially is you're adding an integer multiple of pi on that. So if I do this, let me show you what else you could do. Okay, so let's trace the first solution, pi over 6, and let's add pi times 1. Let's say k is 1. We'll just add pi to it. Well, that's going to end up giving you that solution there, see. Okay, now go to the second one. Okay, start by tracing pi over 3, and again, add pi to it. So if you add pi to it, that will generate this solution here. So basically, if you added 2 pi, then you would get solutions further out here. If you added 3 pi, you would get solutions further and so forth. So you can easily go through and do that way. You can verify your answers on a graphing calculator that way then. Okay, so hopefully that makes sense to start with. These problems sometimes a little hard for students to learn, but follow my procedure. That's really important. Okay, make sure you isolate first. This one's already isolated, so what we're going to do on this is we're going to do the inverse tangent of both sides of this equation. Okay, so we want to get this done. And then again, we'll interpret on the unit circle when we do this then. Okay? All right, so what's going to happen on this then is the left side, what's the left side going to become? Yeah, that's 4x. Okay? We got to find where the tangent is 0. Okay? Tangent is going to be 0 at these 2 points. The reason being the tangent is y over x. And if you go here, y over x would be 0 over 1, therefore it would be 0. So the tangent of 0 radians is 0. And over here, 0 over -1 is also 0. So what you would get is the first answer would be 0. Now, you do something different on a tangent. What is the period of just a basic tangent? Okay, that's pi, so you say pi k to begin with, where k is some integer value. And then the second solution we would have is 4x equals pi plus pi k, where k is an integer. Okay, then what we're going to do is solve these equations for x. Okay, so the difference on this is you use pi k to start with. Now if we divide both sides of this equation by 4 and do the same thing, we can kind of solve both of these equations at the same time, then this is what you would get. You would end up getting x equals 0. So you would just end up with pi k over 4, where k is an integer. So that would be a formula that would generate the answers to this equation. Okay, right there. So what I want to show you on this one is, like we talked about on a tangent, this second one is really unnecessary because this formula will generate every solution that will. So that's your answer to your problem right there. That's it. Okay. Now let's do a quick checkaroo on this one, and I'll show you kind of what you would do on this. Okay, so this time we're just going to graph in y1, we're going to do the tangent of 4x. And not going to do anything with y2 because this is set equal to 0. And we could probably use the same window. I bet we're going to get a whole bunch of different periods of this. That's like overkill, like that. So, okay, we can trace out the first answer. The first answer is pi over 4, okay, right here. So if I traced at pi over 4, okay, that's given that solution, see? So that's good. And where did everything go? Everything got shifted up, okay, and so forth. So you basically would get the same answers after you did that then. I don't know what happened on that and why everything disappeared, so I guess that's okay. It's just crazy. Okay, I'm going to close OneNote and reopen it and see if it goes back to normal. Come on, OneNote, open up. Yeah, everything's back to normal. That's OneNote for you. Okay, so anyway, you got the answer to that, and a couple of things I want to show you on these two problems. There's two things I want to show you on this that are fairly important. I'm going to erase some of this scribbling there. So on the first problem, remember the period. The formula for a sine is 2 pi over b. Well, in this problem, b is equal to 2, so you would end up having 2 pi over 2, so you'd have pi. So I want you to notice that the period of pi shows up in your formula right here. So that's what that pi k is representing in that problem. In this particular problem, the period of a tangent has the formula pi over b. In this problem, b is 4, so you'd have pi over 4. So again, that shows up right there when you have that plus pi k over 4. So it shows up. So the period is changing on these graphs, and that's going to be a part of your formula. Okay? All right, so far so good, hopefully. Okay, next problem. Well, now what we're going to do on this next problem is we're going to get all of the solutions on this interval. So that interval is 0 to 2 pi. So we're going to get all of the radian answers from 0 to 2 pi. Now it turns out this problem right here has a lot of solutions. In fact, it's going to have 8 solutions, and I'll explain why as I go through the problem. Okay, step 1, what we need to do is we need to isolate. Let me zoom on this a little bit so I can see what I'm doing. So you want to go ahead and divide both sides of your equation by 2 root 3. And that's going to end up giving me the cosine of 4x is equal to 3 over 2 root 3. Now, you need to rationalize this denominator. It's important that you rationalize, because if you didn't rationalize, you wouldn't be able to probably understand where this solution falls on the unit circle. So let's multiply by root 3 over root 3. Okay, when you do that, the numerator is going to be 3 root 3. The denominator is going to be 2 times 3. Again, the square root of 3 times square root of 3 is 3. That's going to cross that out. So you're going to end up with root 3 over 2. So let's just rewrite what we have. We have cosine of 4x is equal to square root of 3 over 2. Now I'm ready to do an inverse cosine of both sides. That's why I left a little space in front of that root 3 over 2. Okay. So next step is take the inverse cosine of both sides of this equation. Okay, like that. So what's the left side? Okay, that's 4x. Right side, find on the unit circle where the cosine is root 3 over 2 in radians. So it happens in 2 places. Cosine's the x value. So pi over 6 and 11 pi over 6 is where it happens. So the first solution we're going to write to begin with, pi over 6 plus 2 pi k. That's because the period of a basic cosine is 2 pi. Then we'll have k is some integer value. The second solution will have 4x equals 11 pi over 6 plus 2 pi k, where k is an integer. So we're going to start by getting a formula, then we'll start getting the specific solutions on the problem then. Okay, so we got to solve for x. Dividing by 4, it's better probably to multiply both sides of this equation by 1/4. And we'll just do this on both of these equations while we're at it. We're going to do the same thing to solve both of those equations. Okay, so what will happen is the 4's cross out, and we're left with x. Careful on this side, that's going to be pi over 24. Then if you do this, you would have, if you do 1/4 times 2 pi k, well, the 2 over 4 reduces to a half. So this is going to give you pi k over 2. That's going to represent the period of cosine of 4x is actually pi over 2. So k would be an integer. Okay, now that will give me the basic formula solution to that problem. I'm going to circle that. That's not the solution to the problem, but it's a formula that's going to give us some of our solutions. Okay, if we go down the next one, same thing, solve for x. Okay, this time it's going to be 11 pi over 24. And again, same thing, if you take 1/4 of 2, you get pi k over 2, where k is some integer. Okay, so those are going to be the 2 formulas that you end up with. So now what we're going to do is now we're going to start generating all of these solutions. I'm going to put the unit circle to rest over here. I don't really, probably not going to even need it anymore on this problem. Okay. Okay, so those are the formula solutions. Now we're supposed to get specific solutions. So watch carefully how I do this, and I'm going to end up showing you a shortcut. Okay, so let's start with k equals 0, and let's work with this first solution. So what you would have is k equals pi over 24 plus pi times 0 over 2. Okay, that's going to give our first solution. Of course, that goes to 0, so our first solution is going to be pi over 24, not pi over 4, pi over 24. Okay, so that's it. Okay, now we're going to go to k equals 1. So we'll have x equals pi over 24. Again, I'm doing what this formula tells me to do, plus pi times 1 over 2. Now I got to get a common denominator when I do this then. Okay, so I'm going to multiply the common denominator of 2 and 24 is 24, so I need to multiply this by 12 over 12. Okay, when I get this, I'm going to end up having pi over 24 plus 12 pi over 24. So the next solution is 13 pi over 24. Okay, like that. And again, what you would do is now you would go to k equals 2, and you would do the same thing. And you would go to k equals 3, and so forth until your answer got bigger than 2 pi, because we don't want our answers to be bigger than 2 pi. Well, there's an easier way. Okay, what you're going to notice on this is really all you're going to do is you're going to add 12 pi to the numerator. That numerator got bigger by 12 pi. Notice that pi plus 12 pi gave 13 pi. So when you go to the next answer, what you're going to do is you're just going to do 13 pi over 24 plus 12 pi over 24. Okay, so that's going to give you, that is 25 pi over 24. So that is a third solution. 25 over 24 isn't 2. It's still smaller than 2, so it gives that. Okay, then what we're going to do is 25 pi over 24 plus 12 pi over 24, and then that will give me 37 pi over 24. So that gives you a fourth solution. Okay? All right, now I'm going to keep going one more time and show you what happens on this. So if I now did 37 pi over 24 plus 12 pi over 24, I would actually get 49 pi over 24, and that's bigger than 2. 49 over 24 is bigger than 2, so you just cross that out. That's too big. If you don't know that, you could take a calculator if you had to. I hope you wouldn't have to do a calculator on that, but if you did 49 over 24, you get something slightly bigger than 2. So that's bigger than 2 pi, see? Okay? So that's 4 of our solutions. Now we start over again and we start working with this one now. So again, we start with k is 0, but we work with this formula. So that would be x equals 11 pi over 24 plus pi times 0 over 2, k 0. So that would give you another solution. This is solution number 5. That's going to be 11 pi over 24. All right? Now, a similar thing is going to happen. When you go to k equals 1, you're going to have x equals 11 pi over 24 plus pi times 1 over 2 to begin with. You're going to get a common denominator just like you did the last time. And notice what you're going to get is you're going to get 11 pi over 24 plus 12 pi over 24. So that is going to give 23 pi over 24. And you're going to get the same thing. See, what's happening is these numerators are just getting bigger by 12 pi. So now the rest of them, you can actually do the rest of the answers in your head if you want to. So now you would have 23 pi over 24 plus 12 pi over 24 would generate a 35 pi over 24. So that would be solution number 7. Okay. And then finally, we would do 35 pi over 24 plus 12 pi over 24 to get, what is that, 30... Am I on the right track here? Yeah, 23... Yeah, I'm okay. So that would end up being right here. That would be 47 pi. Okay, I thought I was doing something wrong. So that's 47 pi over 24. So we got that. Okay. Now notice if we did 47 pi over 24 plus 12 pi over 24, we would end up getting 59 pi over 24, which is bigger than 2 pi, so we don't use that. All right, so if we put this all together, these are the answers to this problem. Okay, I'm just going to kind of write them all together here. We have 8 solutions. Who cares what order? We're going to say pi over 24, 13 pi over 24, 25 pi over 24, 37 pi over 24, and then we get down to 11 pi over 24, 23 pi over 24, 35 pi over 24, 47 pi over 24. Those are the 8 answers to this problem, and I'll explain how I knew there was 8 in just a minute. Okay, so that would give and generate all of the solutions to that very equation right there. That's how you do that. Sometimes you will get lots of solutions. I can't imagine I would ever give you a problem where you would have more solutions than this. Kind of becomes redundant, but the concept is the same on how you solve these. So this one is also worth checking on the calculator, so why don't you run through this with me? And you can always pause if you need to kind of get caught up on that. So what I'm going to do is I'm going to put in 2 root 3 times cosine of 4x. Well, I'm being radian mode when we do this now, so we got that. And then the other side is 3. So we want to go ahead and get, that put in. And then as far as the window, since we're solving from 0 to 2 pi, on this problem, let's just go from 0 to 2 pi, because we are getting specific solutions on that interval. You can scale by pi over 2 if you want to, or whatever you want to. And then this time, since we have 3, we probably need to go up maybe to 5 or something like that. That's a pretty good viewing window like that. Okay? All right, now I'm going to move over here just for a second, so you can get everything put in if you need to. Okay, so we got that put in. This is the viewing window that we put in. Now we're ready to do our graph. And what you're going to get is the second graph, y equals 3, is going to come out. So if you look at the solutions that are showing up on the calculator, there are 8 solutions. And this would be where they intersect. So if you look at this, you'd have 1, 2, 3, 4, 5, 6, 7, 8. There's 8 intersection points right there. So what you can do is trace them. I'm not going to trace them all. I'm going to trace maybe the first 3 and just show you. So we trace at pi over 24. Okay, notice, come on, what did I do? Must have put something wrong in there. Yeah, I didn't put a pi in there. Okay, so let's trace at pi over 24 and see if that doesn't work. Okay, that works. That gives you y equals 3. Take the next one, 13 pi over 24, and so forth. Okay, and that gives you that one. And then the 25 over 24 would be this one and so forth. You can trace every single one if you want to. Let's do the 11 pi over 24. So if I do 11 pi over 24, it'll trace out as well. Okay, that one's that. So you can go through and take the time to trace all 8 of them if you want to, and you're okay. But notice on this, the key thing is, these numerators go up by 12 pi. So you can make generating those solutions fairly easy if you notice that. Okay. All right, so that'll take care of that. Pause if you need to. Now I'm going to go down to this problem. And on this problem, we're going to solve in degrees. So this time I want degree answers. Okay. All right, and between 0 and 360. So step 1 is to isolate, of course. So we need to subtract 1 from both sides of the equation. So you would start by having tangent of x over 2 is equal to -1. Then you want to do the inverse tangent of both sides of the equation. And then we'll need to look up the unit circle and see what we got. Okay, so notice I'm starting these problems always the same way. So what's the value of the left side? Okay, that's x over 2. Now we need to look at our unit circle carefully and kind of figure out what's going on here. So remember, the tangent is y over x. We're trying to figure y over x is -1. There are 2 places on the unit circle where the ratio for the tangent's -1. One of them is here, the other one's there. So if you take y over x at both of those places, you get -1. In degrees, you have 135 and you have 315. So the first solution I'm going to write is 135 degrees. Now remember, the period of the tangent is pi, but that's also the same as 180 degrees. So we're going to use 180 degrees times k. All right, then we're going to solve that equation. So we're going to solve this equation by multiplying both sides by 2. Okay, and remember, k is an integer, so I really need to squeeze that on there. Okay, that'll cross out the 2's. You're now solved for x. So now if you do 135 times 2, that's going to give 270 degrees. 2 times 180 is 360 degrees. That's what the period of tangent of x over 2 is it's changed from 180 to 360. Then we have k is an integer. Okay. Now what you're going to find on the next solution you would have x over 2 is equal to 315 degrees plus 180 degrees k, where k is an integer. If you did this, you're going to find that you're going to be out of range when you do this. So that's going to leave you x equals, and let's see, that would be 630 degrees plus 360 degrees k. So that's too big. 630 is out of range. So now we're ready to just generate solutions. So what we do is, this is the formula that's going to work. On a tangent, the second one is unnecessary because this would generate that 630 anyway on that. So if you notice on here, if you did 270 plus 360, you would end up getting 630 anyway. So now what we do is we just do this. So now it's real simple. We just do k is 0, which you can do in your head. That would be x is 270 plus 360 times 0. Therefore, x is 270 degrees would be an answer to that problem. Okay. Now what we'd want to do is go on to k equals 1. Okay, so then you would have 270 degrees plus 360 times 1. Again, I'm replacing k with 1. So that would be x equals 630, which is too big. So the only answer to this problem is 270 degrees. That's it. Okay, that's the answer. Just one answer on that. Okay. All right, let's check this on the calculator. And the way this is going to go, I'm going to wipe everything else from the last problem. y1, I'm going to put in tangent of x over 2 plus 1. And since the right side's 0, I'm not going to put anything in y2. I could put 0 there if you wanted me to. And then I'm going to just change my calculator to degree mode. Okay, and then my window, I'm going to go 0 to 360. I can scale by whatever I want to. I'm going to scale by 90. And then this is probably an okay window for checking purposes on this then. Okay, so what I have is I had you put in this information. So we have that. Now let's graph it in degree mode. And what we're going to see on this, the answer is 270. That's what 270 is right there. So that intersection point between tangent x over 2 plus 1 and the y-axis 0 only occurs at 270. So I could trace it 270, and that right there verifies that that's the right answer to the problem, say. Okay, so that's it. That's all you got to do. All right, okay, so I'm going to put you to work on some problems then. Let's go down to the next thing here. You can pause right now if you need to study what I did. Otherwise, move on. I'll pause the video, and then we'll try to do these two problems here, okay? Okay, so let's check the details on this and see how you did. The answer to the first one, you should have these formulas. X is pi over 6 plus pi k. K is an integer. X equals 5 pi over 6 plus pi k. K is an integer. Okay? And again, what I did on that is it's already isolated. I did the inverse cosine of both sides. That gives 2x equals inverse cosine of 1/2. On the unit circle, the cosine is 1/2 at pi over 3 and 5 pi over 3. So notice in my original equations, I did pi over 3 plus 2 pi k, and then I did 5 pi over 3 plus 2 pi k like that. I solve for x, so I multiply by 1/2. That would give x is pi over 6 plus pi k. So the period, remember the period is 2 pi over 2, since b is 2 in this problem, so you get pi. That's why you end up with that pi k in your answer. So that's how you would get the answers like that, and all I want is the formula answer so you don't generate the specific solutions. Okay, the next one, I don't know how many people thought to do this, but this is what I do. It's easier to work with a tangent. So notice I just changed the problem to tangent of 5x is 1 over root 3. Then I did the inverse tangent of both sides. So I got this, 5x equals inverse tangent 1 over 3. There's actually two places where this happens on a unit circle. You would have the first place where the inverse tangent, the tangent would be 1 over root 3 would be here, because 1/2 over square root of 3 over 2 is going to give you 1 over square root of 3. And the other place would be over, over here at 4 pi over 3. No, not that. Okay, you're trying to get a positive, so that would be, hold on, did I do that right? Yeah, that's pi, yeah, that's 1 over, y over x would work at pi over 6, okay? So we got that. The other one's is not necessary. It would be here. I think I wrote this down on my solutions. I sure did. It doesn't matter, though. This one actually should have been this. So that second one, you would have 7 pi over 6 to begin with, like that. Okay? So you got pi over 6, then you got 7 pi over 6. Okay, showing up on the unit circle. Well, I multiplied both sides by 1/5. That crosses out the 5. This would be pi over 30 plus pi over 5k. So that would be the formula that actually generates all the solutions. What happens on this next one is when you solve this, you would end up getting 7 pi over 30 plus pi k over 5. Well, this formula would generate this anyway. If you got common denominator, so this one's unnecessary. That's the way it works on the tangent. Now let me go over the checking on this. If you're interested in the checking, what I did on problem number 1 is I did this. I put in cosine of 2x and 1/2. I set up a basic viewing window on here going 0 to 2 pi. 0 to 2 pi by pi over 2. So I graphed that in radian mode and just traced out the answer. So really the key thing on this would be to see that we have 5 pi over 6 and pi over 6. So I just traced out the first two solutions and they were right. So this one is pi over 6, and then the second one is 5 pi over 6. Okay, so if you get trace out the first two solutions, then if you got the period right, then you're going to be okay with that. So that's how the graphical check would go. The other one, I did this. Now, what we were solving, we were solving the equation cotangent of 5x equals square root of 3, I think was the original equation. Yeah. Okay, so what I did is I graphed the cotangent by doing this, say. So that is just 1 over tangent of 5x. Then I graphed square root of 3. I used this viewing window. I changed from 0 to pi over 4. And then I did this, and then I just traced out the solutions. The first solution actually was pi over 30. That's all that matters. The rest of them will follow. Okay? So as long as you have the period correctly. So I'm going to show you one other thing on this then, because I think I've already got this on my graphing calculator. So this is the graph that I did. So I had cotangent of 5x is square root of 3. So if I traced the pi over 30, that'll give me the first intersection point, like that. And see, the period is pi over 5. So now if I trace at pi over 30 plus the period, pi over 5, then I should make it to the next intersection point, and so forth. Okay, so that verifies that that is right. So that's what you should have got on this, is those solutions. Okay, so we're going to do one more thing. I'm going to move you down to problem 3 and have you work this one out. This time what I want you to do is get the specific solutions on this. So you're going to start by getting a formula. Then I want you to get all of the solutions from 0 to 2 pi. Go ahead and do that, and I'll close off this part of the video. Okay, so you should have got 4 solutions on this. The solutions are pi over 12, 13 pi over 12, 5 pi over 12, and 17 pi over 12. Okay, so you can look over what I've done here. I'll kind of talk through this. I showed you also the graph on this. So isolate first, move the 1, divide by 2, so you would get sine of 2x equals a half. Do inverse sine of both sides. That'll give 2x. The sine takes on a value of 1/2 two places, pi over 6 and 5 pi over 6. So I start with pi over 6 plus 2 pi k. Then I do 5 pi over 6 plus 2 pi k. These two answers do matter on a sine. Multiplied by a half, I end up getting x equals pi over 12 plus pi k. So that's the first thing we're going to use to generate answers. The second one, same thing, multiplied by a half, I get 5 pi over 12 plus pi k. So that's the second equation that'll generate answers. And you can see kind of what I did here. I start with k is 0. Just replace k with 0, you get pi over 12. And the next one, k is 1, you have pi over 12 plus pi over 1. You get a common denominator, you're really adding 12 pi over 12. So that's 13 pi over 12, like that. Okay, and then it gets too big. So if you have like pi over 12, then up to 13 pi over 12, then you would go up to 25 pi over 12, but that's bigger than 2 pi, so you don't use that. And then the same thing applies to this. K is 0, you get 5 pi over 12. K is 1, 17 pi over 12. And if you go to k equals 2, you're getting too big. What would happen on your graph if you put this in, you would see that you get 1, 2, 3, 4 answers where it intercepts the x-axis. Okay, so that'll wrap that up. And those problems right there are, you have to follow the procedure I gave you. If you do that, you'll be okay. All right, good luck.